here for half an hour.
Okay.
But I've been decorating the kitchen all day, and my dinner is just about ready, so I need to drop
All right.
off.
We
But
can't
that's
make you late for dinner. We won't make you late for dinner. But thanks for joining anyway. As for whatever period of time you have, we really appreciate it. Thanks everybody for joining, taking the time out. I tried to put this at a time that worked for everyone, and I think it mostly got folks in. But all right, so I wanted to review what's happened. I've sent agenda around. Let me just share my screen real quick. We'll talk about what's going on in this space, and hopefully get somewhere where Porg can get some value and give some value before he takes off. All right, so this is the third session of the Muscle Neuron team. In the last session, I'm just recapping the agenda. We talked about the chat room for the muscle model, which has had some good traffic. We walked through what's in the muscle model repo. We've been updating the README and improving it so that folks can actually run it. We looked at Joe's LEMS tutorial. I think there's been a comment on that since then. I don't have a lot to say about it this time, but it's probably good to keep moving forward with those comments. Then we started talking about generating IV plots, and there's been some great updates on that stuff, which I want to talk about. We started with an intro to C302 and what that's all about, which is sort of looking at the whole network, zooming out from just the muscle model. And we were scheduling the Synapse Paper Journal Club to better understand the connection between neurons and the muscle cell. And then we actually had that journal club, which I'm looking to here. And we talked all about that paper that was focusing on experiments actually looking at the electrical properties of muscle cell and stimulating them from a neuron. So this time there's additional stuff going on. Just kind of want to report to everybody what we're working on. But I just want to remind everybody that the bread and butter of what we're doing here is we are making a biophysically detailed model of C. elegans muscle, of the synapse between the muscle and the neurons, and the neurons themselves. And that means ion channels. And so Vahid, who's here, who is always, unfortunately, in a low bandwidth connection, so I know that he would want to have a better connection here, but we're going to have him type into the chat as much as possible to make his comments. But Vahid has really been putting forward a lot of strong proposals in this space, and has had quite a lot of effort that he's putting in here. So I feel somewhat guilty stealing his thunder and showing his stuff, but I know that he also can't in the live chat with the bandwidth. So I'm just gonna highlight all the things that are him. Yeah, no, he's done awesome stuff. The only challenge is the connection, which we can't fault him for. So I'm going to be showing off some of the stuff that he's been discussing, and just kind of to update folks and bring folks into the general proposal. But so Vahid has been thinking big about this challenge of ion channels, and as a sort of proposal for sort of a direction that he's going here, he's thinking sort of expansively about models of ion channels, specifically in C. elegans. And so he's built this this repo, which is just the sort of the beginning of this direction. He's sort of calling it channel worm, which is awesome. And so he's been sharing some proposals with me, and I've been encouraging, and this is sort of the product of where this is going. But he's basically saying, so the aim of channel worm is to integrate information and tools related to modeling ion channels in C. elegans for the OpenWorm project. So if you're familiar with this other project, sort of called Channelpedia, and this is not really intended to compete with it or to overthrow it or anything like that, but you'll be aware that there's a resource out there, sort of the only other resource that I'm aware of that's really been doing work to integrate information about ion channels. And this is an awesome resource, and we love the stuff that's in here. But I think the idea is to get even more focused, because this is sort of generally across all mammals, or sort of all ion channels, but I think there's sort of a bent more towards mammals, which is fine and great, because this is, I think, originally started by a Cortex project. But here, the idea is to kind of focus this down even further into exactly the ion channels that we're talking about for the OpenWorm project. And since it is a complicated enough topic, I think this is a good idea to sort of at least see what we can do and kind of refocus our efforts on this. So Veed's done a nice job of listing out what the objectives are. So manage information, from genotype to phenotype of those ion channels, develop APIs for accessing them, keep data up to date. Then the ion channel modeling, build the models for ion channels based on experimental patch clamp studies, estimate kinetics, create verification and validation tests to prove matching of the models with experimental data, and then setting up a simulation environment, simulating the computational analyses, simulating and running customized versions, and check if the simulation fits the biological boundaries. So all awesome stuff. Here are the use cases. So you can probably see this is like a nice generalization of what we're trying to do specifically for one muscle cell, but thinking about it more broadly as we kind of need to do for the C. elegans. So and this is building on NeuroML format and simulations and LEMS, and giving us the ability to run verified models in the web with Geppetto, which is awesome. So I like this. This is like a nice cross-cutting example of what's possible here. And a lot of the things that are going into this, Vahid has also been listing out online on sort of other issues that we've had in the muscle model issues. And these are really the ones that we are now kind of coming down to here. So in as far as it's great to have the general picture, there's some very specific things that have come out of our last discussions. Just want to remind folks of. So this is an issue where we're talking about basically making a unit test that verifies a correct current voltage curve for the CA Boyle NML2 channel, and this is kind of building on where we've started from the Boyle and Cohen model and the ion channel in there, the scripts that have been written by folks like Rayner and Porig to help us analyze those, the scripts that are coming out of the Channelpedia examples. But this issue is intended to kind of wrap all of that up together and close the loop on making sure that the IV curve that comes out of this NML2 channel is actually what we're getting from the paper. So the paper obviously shows us this figure, and our model produces output. And so we've had a few folks that have been working on it, so a couple things to note. Rick Gherkin has been commenting on this issue. He's coming from the SciUnit world, which is looking at the ability to make unit tests from scientific data in general, and he's looking at this issue as a good way to get engaged and get involved, and make a great example of the benefits of doing that, which is awesome. And so he's getting down to some practical steps, and he's been, he's also been thinking of, in a cross-cutting way, of just like, amping up Psi units and what he calls Neuron units, which is the specialized version of it, to be able to run NeuroML. And it looks like he's having some challenges, though, just in terms of some numerical stuff. So if folks want to have a look at that, that would sort of move things forward. And then, let's see, so, right. Okay, so, but the basic premise to do that, I wanted to kind of remind everybody, because I think there's a lot of stuff going on, it's getting a little confusing, is there's three basic things that we want to do. We want to collect the data, which we've got in a picture. We want to be able to run the existing model, and then we want to be able to optimize the model to the data to make sure that it's fitting well. In some cases, the first two is enough because the existing model, we already have the parameters. So for the CA Boyle, we already have that. But as we go forward, we're going to be needing to do this optimization, and I wanted to talk a little bit about that in this session. So let me just before I can kind of get into some of the depth and the details of what this is looking like and what are the next steps here. But let me just pause and see if there's comment from folks that are in here about any of this, and especially give Porig a chance to speak before he has to run away. So thoughts about this so far, or should I just kind of keep going?
No, it all looks great. It's going to be really useful having just one location for gathering the information about the ion channels, and particularly get a pipeline for putting that information into working models. it's obviously going to be a big challenge. I mean, you can't just, I'm sure, as you know, gather the information and then pop out a set of ion channels and then put those into the neuron, and it will work. But obviously, you do need to gather together what information that is there and have a way of just verifying against that experimental information and producing a working channel model. So yeah, I mean, all this is going to be very useful. So yeah, and yeah, again, as I say, there's tools there for analyzing these channels in NeuroML. Hopefully these will get better and make it much easier to pull out these IV traces in particular. So yeah.
Cool. All right. And I know Joe has several sort of different directions that are kind of based on taking some of this stuff and making and putting it up on the web. And I'm going to show you a couple things as well that might be involved in that sort of like cloud-based pipeline, and it's building on some of the stuff that you've already put out. But and also then for Kadri, who's joining us here, who's coming more from the biology side. So this next piece that I'm going to talk about, I would also direct to you because it comes to sort of working with the data, and this is one of the things where you know, being able to understand the paper and find plots and do stuff with them also would is very helpful, and having biological background and understanding like you know, what the axes are and what the dimensions are, very helpful. So let me sort of talk through that, and by the way, so PyOpenWorm is a destination for the data, but we also have to work on building that pipeline out, and we also have to talk about how that works. But trying to focus on one thing at a time. Okay, so in terms of collecting the data, so I just wanted to highlight some of the recent comments on this as well, also coming from Vahid. So Vahid has, and he sort of, I think, showed this, and we talked briefly about this stuff last time. But so you have a picture, you know, that comes from a paper, and that's all well and good, but it's all pixels, right? And until it becomes numbers that we can actually do a fit against, then we can't do very much. So he's been showing us some tools that we can use to do that, and here's sort of some examples of what this looks like. So he's taken the plot from the Boyle and Cohen paper and has digitized it, and it's come out in this rather nice web tool called Plotly, which basically just gives you a nice zoomy interface to show you the results of data that have been sort of joined together in a line like this. It interfaces with GitHub quite nicely. You can look at the data in an XY plot, and you can also expose that data in various forms. This is the JSON version of it. You can expose it in Python, and MATLAB, and JavaScript, and R, and Julia, and you can nicely link to it. So this is a very nice web way to share data. And how does one create that data was another question I was asking last time. And in fact, so there is this very nice web tool. We featured it out on Twitter earlier last month, I guess. But this is a very nice thing that is actually also an open source tool. It's this web plot digitizer. And basically, it's trying to solve this challenge, exactly the challenge that we have of taking data from raster and turning it into this digitized form that I'm just showing you here. And this is made by this guy, Ankit, who very nicely has open sourced this. And apparently, it's also, you can also run it on Windows, and you can also run it on Chrome, and it is also itself open source on GitHub if you want to contribute to it. So, so just a shout out to that. But basically, you're able to load up a picture, and in here this is just a default picture that they've got, and working your way through the menus, you can actually go ahead and acquire that data, and it actually interfaces directly with Plotly once you're done, so that when you say, you know, save, it directly exports out to Plotly, and you've got your data. So this is awesome, and I think that you know, part of the idea behind being able to gather data and pull it into you know, this general repository is to have a nice chain of provenance from, we know where the figure comes from, we know what paper it comes from, we can identify that, Then, we digitize it, and we have a link to the digitized version, so that's something we have to keep track of. And then we build the model to try to fit that data, and we have a test that runs the model in that way and spits it out. Is there any comments on this? Okay, so let's see. Vahid had something to say. Right now I'm working on the documentation for the data gathering phase and other stuff in the proposed plan and going to publish in the near future. Then I guess we can discuss more on the proposed pipeline. Okay. Ford, did you have something?
No.
Making sense? Okay.
It's all good.
Cool. So this is sort of collecting the data, and so kind of for the first time, we're trying to build this pipeline, and some of it is obviously involves these tools, but now what we're really realizing is that we can there's a human pipeline of effort where we need to kind of build around this, which is identify all the papers, identify all the figures from those papers that we want, clip out those figures, making sure that we know exactly where they're coming from so that we can reference the original authors. Then, digitizing them in this way, keeping track of all the digitized versions, okay, and then building our models to fit on them. So this is a place where I'd like to talk more with folks that are coming from the biology realm to help us with the papers and to help us do this digitizing. And we just kind of need, and what Vahid is saying here is he's basically thinking about that. We need to write up a plan and a essentially tutorial and a guide for how kind of anybody can come in and do this that makes it easy to do. Because right now, yeah, I mean, we're making this pipeline up as we go along, but it does seem very much like what we want to do. And so using this one calcium ion channel, right? We want to make sure that we can have this nice example, because if we can close that off, right? We've got the data, we've got the model. If we can show exactly how that one channel works and how we gathered the data, how we fit to it, then it will serve as a great example for all these other steps, and it'll make us very clear way for other folks to help us do that. Okay, so this is all very good, and I'm really liking where this is going. So now we need to be able to run the existing model. So the other side of this is the model itself. And so again, Vahid in the last few days commented on this. So he's written up this script that generates these IV plots of interest from the NeuromL2 files, and I just wanted to, he's building on Porg's compared to NeuromL script, and this one's actually done in a different way than the ones that we've had before, which is actually rather interesting, where he's actually pulling out all the parameters. So what we had before is that we'd sort of run it, and then we'd pull out the plots, and then we'd filter the plots out so that we'd make the IV curve from different experiments. And this one actually pulls the parameters and then actually calculates the equations to generate the curves and does the math inside this script. So kind of combining what we had in the Hodgkin-Huxley example with pulling from NeuromL2 files, which is pretty interesting, I think. And so this is also something I'd love for Porg to get a chance to look at and see. Do we feel like this is the right way to generate these plots? Would be one question I would have compared to the other one where we're running the simulations as a whole. They're maybe a little bit more ambiguous. I'm not sure. But what I like is this is very clean, and it can all be done in a single script, essentially, without calling out to running full simulations in the time domain and in other simulators. Yeah. So yeah.
Sorry. Yeah. I mean, it is very useful to do this just from the point of view of making sure all those values are correct. But I think, though, in general, I mean, in the longer term, it is useful also to have the NeuromL ion channel actually doing the job of calculating the currents and so on, because basically here, to a certain extent, you're repeating some information. I mean, those powers for x infinity and so on, those are actually in the NeuromL file as well. So say if you had here to the power of 4 and to the power of 2, and it was slightly different in the NeuromL file, you might think, okay, well, it's correct here, but it might be incorrect in the NeuromL file. So that's why I think it's useful to have the facility to actually run the model, calculate current at each time step, and then pull out the current values versus memory potential from that. So a bit, but obviously, I mean, there's some elements of that toolchain that makes it a little bit difficult at the moment to do that. But yeah, but I mean, again, here, one of the main goals of this was to make sure that all the values from the Boyle and Cohen model were correctly translated into the neural.
Okay, so are these values something that could yeah, okay, so it sounds like he agrees. But so these values are in there and could be pulled out, because it was just a matter of like pulling them.
They could be, but I mean, ultimately, even the equation there, the form of the equation could be slightly differently written down here than it is in the NeurML file. So I mean, it will produce a current. If you put a membrane potential across it, it will produce a current in that ion channel, and that's what should be measured. I mean, it's just like in the same thing in a real cell, that you actually do the experiment and then you measure a current and plot it.
Right. Okay. All right. Cool.
But I mean, yeah, don't get me wrong. This is quite useful. So
definitely, yeah. So okay, so very exciting stuff that you know, we're able to do this, and there are some comments about some challenges with this, and so that's generating some to-dos. But nonetheless, I think moving in the right direction. Yeah, so we probably need to figure this stuff out. That Rick's challenge that he's having, but anyway. So then we get to the bottom where we're talking about the data. Okay, so so I just want to talk about those two things. All right. Yeah, go ahead.
Just briefly before you go on, I actually went up to Leeds on Friday and met with Netta Cohen.
Oh, awesome.
Was giving a talk up there, and she appreciates the fact that we're giving life to some of the published models that she has. So she's saying good things, nice things about OpenWorm. So.
Oh, great.
She appreciates all this is being used.
Good. If there were any points of improvement that she had for us, just let me know as well. But that's great. We like hearing nice stuff. We also like any way we can improve. But okay, so you can see then between these two things, right? So here we have a script that generates the plot, right? And then we've got the digitized version of the data. So the whole idea of this create a unit test should be, at this point, just a matter of taking the output of one and doing some math on the digitized version of the other and pulling it into this unit test framework. So it seems like we're pretty close to that, but I just kind of want to highlight that this is not yet done. If we can do that and we can pull it as well into our continuous integration, sort of Travis CI tests, then it's a very nice validation of making sure that model is going to be correct. Because if we go and change it and have different versions down the road, then we want a little test to tell us, hey, we're now no longer fitting correctly. So this is still open, and this is something I think as an example for folks to kind of keep moving forward. I will probably jump in on this if no one else does in a few weeks, just to kind of get to the end conclusion of that. But as you can see from what I've been showing you, we're basically there to be able to do that. It's just literally like one script that does math to do the test.
Okay. Just briefly on that, there is this testing framework, the open source brain model validation tool in Python that Boris Marin wrote.
Yes.
That will does something along these lines. It runs the models on a Travis instance once you commit it, and I think there is in the muscle cell repository examples of this. So you can get it to install JNeurML, to run a JNeurML file, and there are tests built in, ways you can actually test it. It's mainly based around spike times. So a number of the models on Open Source Brain will have tests associated with them, certain spike times that need to be obeyed if you run that model with JNeurML, and also JNeurML or code in Neuron when you run it from JNeurML. And as I say, it's mainly based around spike times, but it can be extended with specific time points in a graph. So say, for example, you had 10 points along that IV curve. You knew the value of V, you knew the value of I, and you can potentially test it with in the same framework with a given tolerance, and hopefully in that way it will comply with those times. those values.
Okay. And should we be looping Boris in on these unit test issues? Because I know, and how does that fit together, or does it yet with what Rick's...
Boris is going to be very busy in the next month. He's having twins, so I think he won't be responding to the requests.
Okay.
I can look into it myself, but I think for the time being, we need, well, ideally, and one of the things I want to try to do next week as well is extend that NeuroMel channel analyzer to actually generate itself the IV curve. So at the moment it's just generating a number of things, the plots for tau and inf and the currents going through the channel. I want to see if I can extend that to also generate a some kind of an IV curve. The only problem is that for example, with this model, there's IV curves for the calcium and potassium.
Yes.
That potassium current voltage plot is for both channels. The way that I've got it set up is that it just analyzes against a single channel. But I can probably do something with the at least the calcium, so that it can be verified against the calcium plot.
Well, let me know what your results are on that, and I can add that work to the tutorial.
Okay, it's preliminary at the moment. Yeah.
Cool.
Once it's stable, yeah, certainly it can be added. But as I say, I'm starting to move things to this PyNeuromL, which is attempting to be a pure Python, or at least a Python module that you can install that will have all these tools in there and can just be one central location for these. But it's slow moving at the moment.
Okay, awesome. I think having a general facility for doing that will be great, and obviously now there's quite a few different examples of how we might do that in the repository and the efforts that folks have been building. So great. Okay, so we've got data and we've got a model, and in the case of the Boyle and Cohen, we had all the parameters. We had all the parameters that they put into their model. And so so there had already been a process that had occurred to pick the parameters, but very soon after we get outside of that, when it comes to any new ion channels, we no longer have all of the parameters, and so this topic of optimizing the model of the data is extremely relevant. And so for that, I just wanted to highlight this comment by Porig, which we haven't really built much on yet, but I think we need to kind of revisit, and this is a great place for folks to kind of get involved. So Vahid had been looking at optimization as well, and Porig was kind of reporting in on the news on what's been happening with the packages for that, and has been talking about a specific preferred pipeline. I guess one question before Porig has to leave is this still the latest, best understanding, or is there a more updated view on how this should work?
I think it is, but I'm starting to work on that with C302 to revive Mike Vella's NeuroTune, which this was originally based on. So again, that's slow moving, but I made a little bit of progress last week. But I want to try to do that in a generic way to make it easy to specify a NeuroML model, specify target behavior, and try, ideally, to pop out an updated set of parameters that can be used in the model. Hopefully get a bit more work done with that, or at the very least point people to an initial version and then ask people to get on board sometime next week.
Okay, but for now, according to this, it looks like the best place to start are with your forks of these two things.
Yeah.
Just if folks want to kind of get involved. Okay. So I would recommend if folks are curious about this stuff that they do that, and we maybe bring this as a bigger topic into the next session, because I think that it's one thing for us to have one set of parameters here, but really there's a whole lot of different combinations of parameters that could give us this, and it's going to matter when we go to the next step, which is tuning the whole topic real quick. So this is the other big issue that I put forward, which is zooming out one level from just the calcium, also the potassium ion channel, and it's also going to involve any leak current that was in there. And so since we've done the journal club, basically I've clipped out the very first figure from that paper and put as a challenge for us all to see if we can get our muscle model to do this. Now this is something that we haven't seen from the Boyle and Cohen paper working, and so because they just didn't choose to fit to this, not because it can't do it or anything, but it is real data. And so this is a place where it's sort of one step reaching beyond what this model was originally built and designed to do, to see if we can replicate something that even starts to look close to the time scale and sort of resting potential of what we have here. And we can probably shoehorn it to do that if we let all parameters go free, right? But the question is, what is the overlap between the parameters that are required to make it do this and the ones that are required to keep it doing what the Boyle and Cohen model, what the Boyle and Cohen paper reports? Is it possible to have it do both? And that's, I think, where it starts to get very interesting, because I think the larger enterprise, what we're trying to do here at the cell level, is to add more and more examples of data like this, present them to our model, and have them pass. And that probably requires doing successive iterative optimizations as we go to fit a larger and larger corpus of data like this. But again, we can see the same pattern that we'll need to do here, which is we're going to need to digitize this. We're going to need to have a run of the model that takes this kind of an input and runs for long enough so that we can see what the output is, and then compare the two, and then also involve optimization that's operating at the level of the cell, not just at the level of the individual channel. So this one's a challenge. It's still an open challenge. Rick started to comment on it, but things that we're going to need, I think, now are going to come out of this playbook, which is we're going to need, number one, to digitize this data, have a link to that digitized data. Number two, somebody's going to need to go in there and have a test run, a definition of a run of the muscle model that that runs for, what is this, like a second or a second and a half or something, and then records the output of it. Somebody's going to need to go in and stimulate it in the square pulse wave. So that all kind of needs to be done here, and obviously I think that needs to I need to enumerate those things more specifically. Maybe break this down into a few smaller, more digestible tasks, so folks have an easier time dealing with it. But that's kind of where we're going. And I know we're sort of just feels like we're inching towards this with just one single cell. But as you can see, there's still a lot of work here. And once we can get it going for one cell and for one complement of ion channels, we've already built a lot of infrastructure that we're going to get to keep building on. So just want to keep highlighting this is the target for where we're going next concretely. Okay.
Okay, I'm going to have to head off, but yeah.
All right.
I'll have a little bit more time I'll have some time next week for looking at these, so I'll hopefully try to give an update sometime during the week on these tools. But again, if somebody does have any questions about the model or anything related to NeuroML, please do bug me. I have a build-up of various things, but if something is stuck on anybody, just keep bugging me and letting me know, and I'll eventually get back.
Cool. Thank you very much. Have a great dinner.
Okay, thanks. See you guys.
Yep. Okay. And right, so that's data from the paper from the Synapse Journal Club. So I explained that data and what this is exactly in great detail over there. So if you need to refresh your memory, I probably talk about it in the first 10 minutes or so, and so that's there. Okay, I also wanted to highlight that the muscle model sample is now part of Geppetto in the dropdown, and let me just do a little bit of a tour of what's there. This just came out in the latest version. The Geppetto team just released recently. So now, if you go to live.geppetto.org and you scroll down to this OpenWorm C. elegans muscle model and click here, first thing to note is where is this actually coming from. So you can see the URL that's being pulled in here. It's coming from, this has been put into the Geppetto samples directory, but it is also under OpenWorm, so you can go check it out. It is under the development branch right now. And so what is it actually pulling in? If we go to this URL real quick here, we can look under the hood. So this is the XML file that defines the sample as a whole. We have to actually go once. Go in, okay. So this defines the LEMS file, right? So that's why we've been working with LEMS, because it can be read by lots of different stuff. But of course, this is defining the simulation sort of parameters and how that works rather than the model itself. So we have to go one more step to get to the actual model, and that's under here. It's been included. So we can go check that out. And this, of course, also pulls in other stuff. So this pulls in a CA Boyle channel. This pulls in the single comp muscle cell. This kind of integrates everything together. Looks like we're defining some pulses here as well. And okay, right. And then this, right, that's right. So the thing that this does is it doesn't just have the muscle cell. It also defines a neuron, and it also defines a synapse between the neuron and the muscle cell. So just one simple neuron between them with a given synapse. And of course, as we know, we're not in any way done with this, but what's cool is that this is now a staging area for this. So I do encourage you to go and dig through what this is pointing at, and because we can start doing pull requests into the Geppetto samples as well when we have versions that are better. But anyway, so what does that actually look like? So if you actually run it under Geppetto, so the visualization, okay, let me just kind of pause this first. Okay, so there is a 3D visualization of this. I think we can continue to improve it. There is the Geppetto guys have a definition for how to build a scene in 3 dimensions, which is another topic. But anyway, so basically there's this cylinder that's here, and there's a sphere that's down over there. And if you click on this, you can see there's a line connecting them together, which I believe is the synapse between the two. I'm not actually sure. I think the circle is the neuron and the cylinder is the muscle, but I'm not entirely sure. So I actually did not build this myself. This is sort of what the Geppetto team has put together. But anyway, okay, so here they are. I believe they're supposed to change color depending on the level of stimulation of the muscle as well when it's running. So that's there. And then when it starts up, there's some pre-made plots, which are also defined, by the way, in the XML. And there's the voltage response of the muscle. There's the calcium concentration in the muscle, and there's the voltage response of the neuron that's defined by those. And then down here is this tree visualizer, which is intended to let you browse the structure of the model that's there. So it looks like there's an electrical component of the model. So some of these have stuff under them by default and some don't. I think that we need to, I think there's an extra command that may need to be issued to load this up. So that might be one thing to improve on this as well, is to have more loaded by default. But then the neuron and the muscle both also have electrical components. There's something describing the connection to the muscle and the connection from the neuron. The muscle also has its own electrical tree. Again, nothing loaded under the model one or the visualization one. There is, under the simulation tree, a single comp muscle cell that looks like it contains the voltage and the calcium concentration values that are, by default loaded to look at, which drives the visualizations that are under here. When you run it, not a lot happens for some period of time, and I think this may be because the stimulation is either delayed or it starts in the neuron and then later goes, well, I guess it doesn't really even start in the neuron. But if you are patient and you wait for some time, you will see some activity begin. I don't know if it's after, yeah, like 0.1 seconds or something. We may just leave it running. It's also, I think, maybe running a little slow because I'm doing the hangout here. But at some point, it will start to deflect, and there will start to be some activity occurring in the muscle model, which is cool, because then we can see it up here online. That said, I think we do need to improve this as well. Okay, here we go. Starting. The voltage response is starting in the neuron. Slowly, 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 slowly. Building up. It looks like it will start to influence the response in the muscle a little bit later, once it builds up to a certain point. But it at least shows a system that has a neuron and a muscle that is running here on the web. And I'm sure that when we have folks from the Geppetto team explain to us better what's going on in here, then we can find ways to improve it too. But anyway, it is, okay, here we go. So then there's this deflection, right. So at some point here, there's this thing where it drops, and this then seems to create this big response in the muscle right now, which is kind of interesting. Doesn't seem to change the calcium concentration in the muscle, though, which is strange, even though this number is changing over here. So, okay, this is a first version. I think it needs to. We need to find ways to, maybe issue some improvements to this. But it's all out there in the open. It's under the GitHub repository for the Geppetto samples. And I think the more that we improve it here, the more that we'll be exposing the work that we're doing on the modeling side to more and more folks, because yeah, anybody can run this right now. Even though it's not perfect, the fact that everybody can run it, I think, is cool. So any comments on that, folks? Okay. All right. So we'll close that off now. So I'll get back to CPU. All right. Oh yeah, and I also wanted to mention, right, the decision-making circuit that folks have been working on is also being integrated in Geppetto, and there's some cool stuff going on with multiple neurons and connections between them, which will be very cool when that's in there. But it's not quite there yet. Okay, last thing under this is under PyOpenWorm. There was some discussion about databases and spreadsheets under this in a meeting that folks had on Gitter. And I just wanted to highlight the great work that's going on over here with PyOpenWorm. So folks like Mark Watts and Travis Jacobs have been getting very close to moving from the alpha 0.5 branch of PyOpenWorm to master. I may have said this last time. It's still not quite done, but it's a lot closer. There's only 5 remaining issues. One of them is a pull request, and the other one, this is like the main pull request, so don't count that one. So it's really these 4. Basically some documentation things and some final bug fixes until this thing moves over. But the point that I was making here is that the connectome that's listed under C302 is now directly being driven into this. And so when we talk about storing the parameters for the ion channels in some form, I think this is going to be a good way to do that. That's nice and synergistic with everything else that's going into this. Is one example that's kind of cool, that's new in here in terms of what you can do with the platform. So in addition to being able to sort of return the list of all neurons, return the set of all muscles, right, which our muscle is going to be in there. You can see which neurons innervate which muscles, right? So you pick a given muscle, and then you ask, like, what are the neurons that innervate it? So when we have, MDL08, which is our muscle, and then we have all the neurons that go into it, then you can easily get a set of what those are. And if you could go one step further, right, which we kind of do, we have receptors up here, right? You say, oh, well, what are all then the receptors of all those neurons? Then you get, a receptor, could also be an ion channel. And then you could drill in one step further and say, hey, what are all the parameters of that ion channel? And then output that to NeuroML and give me the NeuroML and LEMS description of that. So this is all being built here under the hood, and I just encourage folks to keep looking at the progress on this and watch for the announcement when it gets pushed to master. But folks can be playing with it now on the alpha branch. Okay. That's my main agenda then for the moment. Do folks here want to make any comments on this, or think about like how we can practically move forward with next steps, or Joe, I know you're looking to kind of get re-engaged. Does any of this re-engage you, or does it give you ideas for what you'd like to do?
Well, I've got things on my plate, so I just need to re-engage. That's me.
Okay.
I apologize for it, but with the new job, I'm a little swamped at the moment. I'm hoping things settle down and I can get back into the swing of the things here. Some of the things my thought was on the tutorial with adding the Geppetto section of it, there was a suggestion to use open source brain, which I just need to set up. So I'm just going to do that. So that's issue 6. Here I can copy that one here.
Okay.
And on the other side of things, I've still got the movement validation, but I'm not worrying about that now. On the muscle, for the muscle kind of cloud thing application, I think we might want to wait a little bit until we hash out exactly how the whole paper to model
Pipeline.
steps. Yeah, pipeline is going to look. Yeah.
Okay.
I think because really the cloud will it'll integrate all those tools. So I think trying to build the cloud before the tools are built would just be pointless, or putting the cart before the horse.
Okay.
So I think I've got enough on my plate for right now. If there's anything I can kind of help with, that anyone has any questions, I can pitch in here and there.
Okay.
But, yeah, that's my plan.
All right. Very good. Well, yeah, don't burn yourself out.
Trying not to do that. Yeah.
It's a volunteer thing, so obviously you got to take care of other stuff first. And this just goes for everybody. Like, just finding one little thing to do or one comment to make, is great. Just to stay engaged. It's better to do little things, regularly than to you don't have to impress us with any huge thing. So don't worry about that. Like, we're not tapping our foot or anything like that. You've already made awesome contributions. So don't feel guilty or anything. Which I think somehow it's easy for folks to sort of feel worried that they haven't contributed. But
yeah, not worried, but I enjoy this. So and I like helping the scientific community. So I'm, it's for me.
Cool, good stuff. Yeah. Okay, and Kadri, I don't know if you're still hearing me here. If you do have any other additional comments you want to make here in the chat, I think that we should probably make an issue for us to capture this documentation, the data gathering phase that Vahid is talking about here, just to have a handle on it. So Vahid, we probably, and I guess it also kind of comes out of what I'm talking about with the muscle model. I think since maybe it's still a little abstract as to how to go about doing some of these steps, I'm going to try to make these a bit more concrete to say, okay, let's list out 2 or 3 specific papers, which I think Vahid has already identified several papers. Let's say exactly which figures. Let's say exactly how we go about digitizing them. This kind of thing. Let's see if we can go from the abstract to the concrete kind of 1, 2, 3, 4. And then if folks like Kadri and I think Emma also from last time coming in from the biology side can help us with some of that and know where to put it, I think then we can get even better collaboration going. So I think that would be good. Yeah, the more that we express this stuff in issues, the better. And let's also keep the conversation going on the Gitter channel because then we know where everybody's at. Okay, not able to hear everything. Uh-oh, that's a problem. All right, Kadri. Well, this will all be archived up on YouTube and for everybody else as well. And then probably the streaming from YouTube will be a little bit better because you can let it buffer. So if it basically, yeah, we want to have this documentation written up so that you can sort of come in and help us with some figures. I think would be the main next step. So let's try and get something together for her. Okay, guys. Well, this was a shorter meeting than we had planned out for, so I thought maybe we'd get a few more folks in, but we will next time. We're shooting it about once a month for this, and I'll try to keep reporting on what's been happening so that we kind of get a big picture again. And but we've made a ton of progress in the last month. Thank you again to Vahid in particular for driving this and pushing forward so much. I'm actually trying to keep up with you, which is great. It's a great place to be, and I think that this is consonant with work that he's doing as well. You know, for his own graduate work too. So there's some excellent synergy going on. So let's take this now to the chat from here forward. I'll make some of these things more concrete, and I'll send around a poll in about another 3 weeks or so to get a good time for us to chat some more. Okay.
Have a good one, everyone.
Awesome. Thanks, guys. Have a great rest of your weekend, and see you next time.